Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is estimating PV system performance using NREL solar radiation data sheets. Our objective today is to familiarize ourselves with the Solar Radiation Data Manual for flat plate and concentrating collectors produced by the National Renewable Energy Laboratory's Renewable Resource Data Center. We'll use peak sun hour data found on these data sheets to estimate PV system performance. Along the way, we'll briefly discuss dual-axis trackers, single-axis trackers, fixed mount systems, and briefly hit on array sizing. Since the 47-syllable term National Renewable Energy Laboratory Renewable Resource Data Center Solar Radiation Data Manual for Flat Plate and Concentrating Collectors does not easily roll off the tongue, we'll content ourselves with the initials NREL, RREDC. It's easy to see how the Solar Radiation Data Manual then got abbreviated into NREL Redbook data. Be aware, it's not red, nor is it a book. It's information that's freely available on this thing called the Internet. Perhaps you've heard of it. Once I get the BigBadTech.com website actually up and running in like a million years, I'll try to provide a direct link to this data. Till then, you're on your own. If you don't know how to use Google, have an 11-year-old show you how. Bottom line up front, the pertinent data we're looking for inside the NREL Redbook is peak sun hours. If you've never heard the term peak sun hours before, or perhaps only dimly recall its meaning, I definitely recommend you hit the Peak Sun Hours lecture at the Big Bad Tech channel. It's 36 minutes and 38 seconds of sheer thrilling drama, comedy, and action. Don't worry about me, just pause the lecture and I'll be right here looking at pictures of cats on the internet till you get back. Alright, if you're back or never left, let's get on with the show. NREL over the past 30 plus years has been tracking renewable energy resources like solar and wind at 239 sites scattered throughout the US and associated territories. Obtaining the value of peak sun hours for your location is very accurate and very easy if you happen to live in or right next to one of these sites. Outside these regions involves a little guesswork and approximation, or perhaps the use of additional software resources we'll discuss in later lectures, but the 239 sites cover most of the shoe-wearing regions of our country. The sheer volume of data collected over such a long period of time ensures it's not only reliable, but can also be used for the long-term analysis of our climate and recognizing any anthropogenic or naturally induced changes to it. Again, the specific data set we're looking for is the NREL RREDC, Solar Radiation Data Manual for Flat Plate and Concentrating Collectors. Go to the internet, but don't stay too long, and see if you can pull the data for the site nearest you. Easiest way is to search using the term NREL Redbook. Use the datasheet for the NREL site nearest your location to follow along, or just watch me point out data on this one. First and foremost is obviously the name and location of the site. Pendletucky, Oregon, being home of the famous Pendleton Roundup, the infamous letter buckroom, and the densest concentration of sweaty perverts and murderous halfwits in the Pacific Northwest, is located at 45.68 degrees northern latitude and 118.85 degrees western longitude. This is pretty critical, because the latitude and longitude data obviously dictate rise and set times, and most importantly, the rise and set angles at specific times of the year. The header also includes elevation, 456 meters, and average air pressure readings, 963 millibars, that can be useful in calculating air mass data if you want to get into nitnoid detail. An example of air mass differential would be the performance difference between a PV system set up in the Rocky Mountains versus one set up in the fat malarial lowlands of Mississippi. The one in the mountains obviously has less atmosphere between it and space, and therefore less radiant energy will be absorbed by the thin atmosphere. Coincidentally, the owner of the system in the mountains will also statistically stand a better chance to read at a 4th grade level and will most likely not die of obesity-induced heart failure. Yes, Mississippi, I'm making fun of you. Even Alabama makes fun of you. The core of the datasheet contains rows and columns of numerical data. The columns represent months, and all the way on the right-hand side is one column representing annual averages. In addition to the expected values, the datasheets also include minimum and maximum values. These minimum and maximum values remind you that the sun and weather don't care, and they'll do what they please. These numbers are useful in determining worst-case and best-case scenarios, perhaps for mission-critical tasks in off-grid locations. Additionally, notice the plus and minus percentage uncertainty at the head of each dataset. Don't think you can bring legal action against the sun for breach of contract. It's been justly worshipped as a god since the dawn of human history and will most likely strike you dead. Let's skip the center part for now and look at the additional supporting data at the bottom of the page. This is climate conditions, and it shows average temperature data per month as well as annual average on the right-hand side. Additionally, it shows heating and cooling degree days. These are useful numbers in determining the space conditioning energy requirements for a building of a given size. Be aware not all these datasheets are the same. This datasheet also happens to include record low temperatures, which we'll learn is an incredibly important piece of information when calculating open circuit voltage for an array. A very important topic we'll get to in later lectures. Returning back to the core of the datasheet, you'll find 4 datasets divided into solar collectors at a fixed tilt angle, single axis trackers, dual axis trackers, and concentrating collectors. The numbers in the columns are in units of kilowatt hours per meter squared per day and are equivalent to peak sun hours. This is the number you use in addition to the power rating of your array to estimate energy production performance. The differentiation between the 4 datasets obviously refer to the means of mounting PV panels. Regardless, every single one of these datasets assume the PV panels are pointed due south, and alternate orientations need to be accounted for via TOF charts or other means. This topic is covered extensively in the PV system solar site analysis tilt and orientation lecture. The first dataset represents PV panels pointed due south at a fixed tilt angle, and this is the dataset you'll most often use. The angle could be horizontal, meaning flat on its back with a 0-degree tilt angle, or mounted on a wall like a vertically hung picture frame at 90 degrees. Or it could be tilted at latitude, or latitude minus 15 degrees, or latitude plus 15 degrees. We'll return to the importance of these 3 middle angles in a little bit. The second dataset is for a single axis tracker, of which there are 2 types. East-west axis trackers, which tilt up and down to track the elevation of the sun, but do not change orientation, and north-south trackers, which spin to track orientation, but have a fixed tilt angle. If you think about it, an east-west axis tracker actually has a horizontal axis, and it tilts up or down on this horizontal axis to actually follow the sun's north-south changing arc. And a north-south axis tracker actually has a vertical axis, and it spins on this vertical axis, keeping the panel tilt fixed to actually track the sun's east-west arc across the sky. But somebody way smarter than me came up with these terms, so we're stuck with them. The next dataset deals with dual axis trackers, which continually track both orientation and elevation of the sun by both revolving and tilting. Realize a flat plate collector uses both the direct and diffuse contributions of light. However, our fourth dataset uses a concentrating collector, which uses only the direct portion of light. Think of a parabolic dish, which concentrates all incoming direct energy to a single point. It must necessarily only use the direct portion of light to focus. Therefore, it must necessarily track the sun if you want it to work more than once a day. Since using only the direct portion, a concentrating collector on a dual axis tracker will have on average less sun hours at this location than a flat plate collector on a dual axis tracker, which uses both the direct and diffuse contributions of light. A brief aside before I continue. Regarding trackers, I'm often asked the question if they're a justified expense. And the answer is most assuredly no, with an asterisk behind it. The asterisk is intended to imply maybe yes. In the rare situation you're absolutely desperate to extract fleeting solar energy, or you're being paid a premium to generate as much renewable energy as possible. Trackers are costly to install and require continual maintenance to operate as intended. Does the added generation outweigh the cost and upkeep? I don't know. It depends on your situation. My recommendation for those considering a tracker to compensate for a poor solar resource is to move your system to a better location. Why are you considering solar in the first place if you live in some dark hollow where the sun refuses to shine? Spend the tracker money on additional panels for a fixed mount system in a sunnier place. Problem solved using no expensive moving parts. This being said, a functional tracker is truly a neat thing to behold and quite obviously represents the optimal means of maximizing energy production. Before we dive into the datasheet, let's briefly discuss tracking. One way to track the sun is through the use of a light sensor, actuators, and a comparison algorithm. The light sensor continually reads light data at the array and attempts to maximize input by allowing the actuators to revolve or tilt it. If the sensor's input is increasing, it's obviously revolving or tilting in the right direction. If the sensor's input is decreasing, it's revolving or tilting in the wrong direction and it must be reversed. Even if it's pointed right at the sun, it'll drive past it just to see if it's sunnier on the other side. What you get is kind of this slow wiggle waggle aimed generally at the sun. Obviously, this isn't a radical thrashing from one extreme to the next, but an optimized and tuned comparison which maintains maximum exposure as the sun moves across the sky. In especially overcast conditions where the light is all diffuse, these trackers aren't especially useful because they're confused as a kid in a roundhouse having been told to pee in the corner. Additionally, one could conceivably hack this type of tracker with a flashlight. Another method of tracking is to simply tell the tracker where it is, what day and time it is, and where you expect the sun to be at a particular date and time, and let it take it from there. Basically, this method uses a predetermined sun path chart, something we'll cover in later lectures, and a continually running clock. When the tracker wakes up, it rolls over, checks the date and time, and looks at the sticky note with the sun path chart on it for that particular day. It spends the rest of the day telling the actuators to revolve or tilt to the correct angles at the correct times to maintain maximum exposure. In this case, overcast conditions aren't a problem because the tracker knows the sun is at a particular orientation and elevation whether it's covered in clouds or not. The problem with this method is that the tracker never actually checks to see if all the revolving and tilting it's doing actually benefits energy harvesting. If a tracker using this method thinks it's midday, midsummer at 20 degrees north latitude, because that's what was loaded upon commissioning, or that is its default setting following a reboot after a power failure, it will not be optimized for mid-morning, mid-winter conditions at 40 degrees north latitude. A truly robust active tracking mechanism will use a combination of both these previous methods. The pre-programmed sun path would ensure the tracker is at least pointing in the right general direction. Then the tuned light sensor would pinpoint the actual position of the sun. Be aware both these methods of tracking require active input from sensors sent to a controller that would drive an actuator like a hydraulic cylinder or an electric motor. Active position maintenance is expensive and requires substantial hardware and control systems. In addition to these direct means, there's another means of doing so, namely by passive means. This method is admittedly somewhat Rube Goldberg-esque, but I give this method credit for sheer ingenuity and out-of-the-box thinking. This method uses a phase change substance inside an enclosed tube. It's a liquid at one temperature and a gas at another temperature. The previous day's tracking would leave the array pointed westward. However, the dawn sunrise strikes the tube and warms it up. The phase change substance heats up and initiates accumulation of the liquid on one side, which at a certain point flips the array back eastward. Over the course of the day, the accumulation of liquid at one end of the tube makes the array passively follow the sun. Once the array has completed that day's tracking, it stops facing westward, ready to initiate the process again. The initial morning sun is not captured because the array isn't facing in the right direction until the tube heats up. Upgrades to this passive tracker include an active flip at night that readies the array for the morning sun. Despite its admittedly cunning passive means, this is not the tracker to use in high wind conditions. Speaking of high winds, in addition to the initial cost and upkeep of trackers, one must consider the longevity in adverse environmental conditions. Sticking a bunch of panels on a pole in high winds is asking for trouble. It's not your soft lawn or empty driveway that'll be hit by a piece of razor-sharp monocrystalline silicon aluminum glass. It'll be your car, your garage, or your neighbor's prize-winning show dog that will be. It's for this reason most modern trackers include stow and snow options. An anemometer wind vane combination can recognize dangerous wind conditions and signal the controller to initiate evasive actions such as turning away or changing the tilt angle until the conditions pass. Additionally, those systems in mountainous winter conditions can start the day with a vertical tilt prior to beginning tracking. This early morning stretch simply dumps the accumulated snow off the panels prior to tracking. No sense following the sun if you're covered with a foot of snow. Returning to our datasheet, we realized that a dual-axis tracker located on the grounds of the Eastern Oregon Correctional Institution in Pendleton, Oregon, would experience an average of 6.5 hours of peak sun every day. Given an array size of, let's say, 2.75 kilowatts, we could easily determine the average daily output for this array. Given the datasheet also includes monthly averages, one can specifically target a given month to see expected daily output for that month. The same array would generate 29.975 kilowatt hours on average on any given day in July at 10.9 hours of peak sunlight, upwards of 33.55 kilowatt hours with a maximum of 12.2 peak hours of sunlight. Now, before all you off-gridders pack your bags and move to Pendleton, pause to consider all the sweaty perverts and murderous halfwits that populate this region, as well as the performance of this same array in December. With only an expected peak sun hour value of 2.2 hours, this same array would produce 6.05 kilowatt hours on an average day in December, downwards of 4.125 kilowatt hours at a minimum exposure of 1.5 peak sun hours. Let's discuss fixed mount configurations facing due south. Again, this is our first portion of the dataset. I tire with Pendleton, so let's swap out data sheets for a town less sweaty and murderous for something more kind and odorous, Eugene, Oregon. Notice the annual averages for all possible configurations of systems are significantly less than the figures we observed for Pendleton. It is immediately evident that Eugene is less sunny than Pendleton. However, you will be statistically less likely to be stabbed in the back with a broken wine bottle here. For a fixed array pointing due south and laid flat on its back with no shading issues, let's say the top of an organic patchouli warehouse, this array would experience on average 3.7 hours of peak sun. However, the same configuration at 0 degrees tilt would experience 6.7 hours in July and only 1 hour in December. Notice the disparity between summer and winter figures for horizontal or flat configuration. The sun is higher in the sky in summer and lower in the sky in winter. Such a configuration would favor production in the summer. If this same array was hung on the south-facing vertical walls of this warehouse, or 90 degrees, it would experience on average 2.7 hours of peak sun. Again, because of the angular difference of summer and winter sun, this array does better in December at 1.5 hours of peak sun than July at 3.1 hours of peak sun. This configuration increases winter production at the expense of summer. Let's rush to judgment and claim that a more horizontal tilt maximizes summer production because of the higher sun, and a more vertical tilt would maximize winter production because of the lower sun. It stands to conjecture that the midpoint between these two extremes would represent the best of both worlds. Eugene is pretty unique in that its latitude is 44.12 degrees north. It's almost halfway between the equator and the North Pole. If we tilted the array at almost halfway between horizontal and vertical, or at the same latitude as this location, we would expect a decent compromise. In July, we experience, on average, 6.2 hours of peak sun. Less than horizontal, but double that of vertical. In December, we experience 1.6 hours, almost the same as our vertical configuration, but just shy of double that of horizontal. This we would expect to represent the optimal configuration, but it isn't. Look at the row immediately above it. This is the row representing a tilt of latitude minus 15 degrees, or roughly 30 degrees. Notice the annual average peak sun hours experienced for this tilt angle is 4.2 hours. It's slightly better than our previous latitude tilt. Why is this true? The answer is surprisingly simple. With a shallower or more laid-back tilt angle, you're slightly favoring production in the summer months when the sun is in the sky longer and each day contains more energy per second to be captured. Yes, there is slightly less sun hours in winter for latitude minus 15, but who cares if you're only considering the annual energy production for a net metering configuration? This is by no means true for all locations or all applications. An example would be an off-grid cabin frequented only in the depths of winter during Sasquatch hunting season. One would purposely tilt the array towards vertical to favor production in a winter environment. Additionally, if you knew anticipated energy requirements, one could purposely size an array for suboptimal winter sun to ensure your battery pack has enough juice to keep the lights on at night and the radio on while you enjoy a hearty meal of Sasquatch liver with a side of fava beans. We'll go over energy budget calculations for off-grid applications in later lectures. Long story short, look at the datasheet for the location nearest you and try to match the tilt angle that maximizes annual energy production. In off-grid environments, you'll most likely need to rely upon backup generation in the depths of winter because it'd be cost prohibitive to assemble an array that powers your needs at all times. First question people ask about NREL Redbook data is what if you don't live next to an NREL site? The answer is quite simple. Approximate. Again, these are estimation tools only. And if your radio and lights cut out mid-Sasquatch hunt, only got yourself to blame because you dorked with the data. Here's a couple guidelines. Are you close to a site? Do your environmental conditions closely match that of a nearby site? If so, use the data from that site. Are you equidistant between two sites? And your climate and environmental conditions represent a perfect blend between the two environments? If so, average the data between the two nearby sites. Are you between two sites, but your environmental conditions more closely match one and not the other? average the data between the two sites, but put in a weighting factor to favor the site that more closely matches your environmental conditions. The weighting factor must be fair and honestly considered. Consider microclimates induced by dramatic terrain. My backyard, the Columbia River Gorge, is a classic example of this. The Cascade Mountains run north to south and clearly separate the wet western half of Cascadia from the dry eastern half. The nearest NREL sites are Portland, Oregon, and Yakima, Washington, representing the west and east side respectively. Consider Hood River, Oregon, almost right on the dividing line. If you're standing on shores of the Columbia looking west, all you see is ferns, Doug firs, and effeminate latte-drinking Prius owners. Look east, all you see is dry hills, scrub oaks, wind turbines, and rootin' rednecks of the reddest variety. Here I'd be confident I could take the equal average between the two sites. Sites further west, like Stevenson, Washington, would definitely favor Portland, or maybe even Barrow, Alaska, if you've ever been to this region of the gorge in the winter. Sites east of here, like the Dalles, Oregon, would favor Yakima, Washington. But not too much though, because I've been to Yakima midsummer, and I swear I saw a hot sidewalk once catch a bum on fire. One could take both datasheets, dump them into Microsoft Excel, and tell Clippy, Microsoft's annoying mascot from the late 90s, to average the dataset, skewing it to favor the easterly or westerly dataset if you so desire. Alternatively, you can use the legacy PVWatts 2 or the updated PVWatts calculator online resource at the NREL website to do the same thing for you. We'll go over these resources as well as the legacy PVWatts 1 in later lectures. For now, let's just keep things simple and say you live next to an NREL site, and we're going to use this data for our analysis. Using your chosen site, see if you can estimate the minimum, expected, and maximum daily performance on a monthly basis for a 3.6 kilowatt array, tilted at latitude -15 and pointing due south. Then use this data to see if you can figure out how this array would do on an annual basis. I don't know where you live, so your figures are going to be obviously different than mine, but the method I use to arrive at this data should be understandable and transferable. You might want to watch me do this the first time to make sure you understand what I'm asking for. Let's say our 3.6 kilowatt array is located in Spokane, Washington. On an average day in January, we'd expect 2.1 sun hours. However, we could expect 1.5 hours on the low side and 2.7 hours on the high side. I know the sun doesn't just shine 2.1 hours on average, but rather the energy content for that day is equivalent to the sun shining at full intensity, or 1000 watts per meter squared, for 2.1 hours. This is the peak sun hour number we'd use to calculate and estimate performance for a 3.6 kilowatt array. Ordinarily, we'd expect our array to produce 7.56 kilowatt hours every day in January. Minimally, we would see 5.4 kilowatt hours, and on a usually bright day, we'd expect to see 9.72 kilowatt hours. Now what we'd have to do is walk through every single month and do the same thing. This is going to get super tedious, super quick, so I'm just going to dump it into Excel and let Clippy do the heavy lifting. Now that we've got daily expected minimum and maximum performance on a monthly basis, how much energy will this array produce in a year? Clippy can help you get this data by simply multiplying the daily outputs by the number of days per month and then just summating the values. In this case, if every day per month behaved exactly like the average, you'd expect the same 3.6 kilowatt array to output 5,935 kilowatt hours. If you had an unbroken string of bad luck for 365 days, after all, you are living in Spokampton, your system would only produce 4,678 kilowatt hours. It may seem like I'm doing this the long way because I'm ignoring the annual average column on the right-hand side of the datasheet and the bottom row in this spreadsheet. If you're looking at a quick snapshot only, one could use this average data to calculate what the array would produce on average and what an average year would look like. In this case, 5,913 kilowatt hours is really close to our tediously calculated 5,935 kilowatt hours. The disparity between the minimum and maximum is because you're really never going to have 365 days of constant minimum exposure and 365 days of constant maximum exposure. Again, the quick snapshot annual average peak sun hours of 4.5 could have been used to calculate the entire annual performance of this array. However, I don't really want to do that because I want to show you something neat that directly relates to the later lectures dealing with shading analysis. Realize for this example we've been calculating performance based off 100% efficiency, which is obviously never going to happen. We can now modify our efficiency column in our spreadsheet that reduces each month's expected output proportionally. If we had a blanket level figure saying our complete system was only 77% efficient, all monthly output would be reduced by the same amount, yielding us only 4,569.9 kilowatt hours annually. If our efficiency was not constant for one of the systems within our cascaded arrangement and varied from month to month, we need to take this into account. This is a preview of the shading analysis lecture, which we'll be getting to shortly, but for now, realizing shading analysis is an efficiency measurement that varies throughout the year. An example would be a large opaque mountain that blocks the low-angle winter sun for a predictable and measurable amount each day. That day's production would have to be reduced accordingly. In addition to familiarizing you with these data sheets, I'm hoping this exercise illustrates the cyclical nature of the sun. It's immediately recognizable and understandable. Tabular numerical data is represented graphically in the upper right-hand corner. Now let's approach this data sheet from a different direction. Let's attempt an array sizing exercise using the same location. Let's say we're looking to provide mission-critical power for an off-grid application in the depths of winter and require a minimum of 10 kilowatt hours energy daily to accomplish it. Assuming 100% efficiency for both our array and charging apparatus, obviously erroneous assumptions. What is the minimum size of the array necessary to accomplish this? Even with 100% efficiency, the answer is going to be way too big for you to afford. Let's say we're looking at the month of December. Assuming the array can be pointed due south with no shading issues, what's the tilt angle you're going to use? You might think 90 degrees, with 2 hours of peak sunlight expected, with a minimum of 1.2 hours and a maximum of 3.2 hours. But realize the row right above it at latitude plus 15 gets us better minimum values. 2 hours expected, 1.3 minimum, 3.2 maximum. Again, it's a mission critical task, meaning you got to take that 1.3 hours. Additionally, be aware this data has a plus or minus 9% uncertainty, and say it has 1.183 hours of peak sunlight. With such a small amount of peak sun hours available, you need an 8.45 kilowatt array to make this happen. Now, taking into account efficiency losses, assuming 77%, realize this same array would have to be close to 11 kilowatts in size. This is monstrous and a costly overkill, when our liberally utilized genset or a well-placed wind turbine could make up the difference in winter months. Consider the overgeneration of this same 11 kilowatt array in summer, still at latitude plus 15 tilt angle on an unusually bright day in September with 6.9 hours of peak sun. Assuming 100% efficiency, this same array would produce 75.7 kilowatt hours in this day, in excess of 7 times the necessary requirement. I suppose this would be a great day to have the in-laws stop by for a visit so they can leave your refrigerator open, the lights on, and take long showers. However, keep in mind this array is sized for the worst day of the year, and any other day than the worst day will overproduce. Do you want your in-laws hanging around that long? I didn't think so either. Alright, I think we've covered enough material for this session and arrived at a point where we need to wrap it up and send you back to the real world feeling like you learned something. In conclusion, we examined the Solar Radiation Data Manual for Flat Plate and Concentrating Collectors produced by the National Renewable Energy Laboratory's Renewable Resource Data Center, alternatively known as the NREL Redbook data. We use the peak sun hour data found on these data sheets to estimate PV system performance. Additionally, we briefly discussed dual-axis trackers, single-axis trackers, and fixed mount systems. Finally, we did a couple exercises to figure out energy production at certain times of the year, briefly introduced shading effects, and discussed array sizing for a given energy requirement. Remember to review this material as often as you need to really drive it home. Imagine how well your PV system will perform if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.